So tree traversals are, I would say, methods of visiting all nodes of a tree, really. I mean, it doesn't have to do anything with a binary search tree. It's just if you have a tree, then this gives you an ordering of all the nodes. So it visits all the nodes of a tree in a specific order. So there are many orderings. I'm not going to talk about all of them, but maybe the most important ones are called inorder, preorder, and postorder traversals. So one can think of this as a way of just methods to print, let's say, the keys of a tree. So the easiest way to sort of explain this is, let me just write out like a small snippet of pseudocode for in-order traversals, and then we can talk about it in some more detail. So let's just think of this as, well, let me not even give it a type. Let me just call it, so the in-order traversal. And as an argument, as usual, because the way to do binary search trees is through recursion, we'll say that there is some start node. Okay, so there are 4 steps. The first step is if start is null, then just return. So there is really nothing to do. Then what we'll do is we'll call an in-order traversal from the left. We'll print key arrow start, start arrow key, not key arrow start. And then we do an in-order traversal from the right side. That's it. It's just 4 steps. Right? The first is a base case, that if the tree is empty, then there is really nothing to do. Otherwise, if you look at this tree and suppose this was start, and of course this might be part of some bigger tree. First, there's a recursive call to the left. Then you print what is it start. Then there's a recursive call to the right. And this is called an in-order traversal. And if you think about it, eventually, if you call this from the root, this method will print all the keys in the tree. Right? Because you just do it recursively from the left child and the right child, and eventually you call it at all nodes of the tree. So this is an in-order traversal. A preorder traversal it's pretty much the same method. You just sort of swap the orders of some of these. So the first step is always the same. In the second step, you actually print. The first thing you do is print what's that start arrow key. Then you call a preorder at start arrow left, and then a preorder at start arrow right. So you always call the left tree before the right tree, but the decision that you make is, do you print first? That would be a preorder. You print in the middle, that is an in-order, and you print at the end, that's a postorder. So a postorder traversal again, the first step is the same. For the second step, we'll recursively call a postorder traversal from the left, then a postorder traversal from the right, and then we'll print. The key. Okay, so these are the three methods. I mean, and the best way to understand this is I will give you a series of questions, and then once you answer those questions, I think you'll start to see what's going on. Does this make sense? So it's just, all I've done is, it's almost like I've taken some permutation of the lines 2, 3, and 4, right? And I always call the left before the right. So there are 3 possible positions for the printing. It could be at line 2, line 3, or line 4. And that gives 3 possibilities, and depending on which one it is, if it's line 2, it's preorder, line 3 is inorder, line 4 is postorder. Okay? It's clear? We have these 3 methods. Now it's time to answer some questions. Which order prints the keys of a binary search tree, or I should say which traversal prints it in sorted order? Okay, which traversal prints the keys of a binary search tree in sorted order? So is it the inorder, the preorder traversal, or the postorder traversal? I'll give you a few minutes to think about it. Does this question make sense? So the best way to do this is to write down a small binary search tree, actually run these methods and see what you get. And you see which one of these methods actually prints it in sorted order. Okay, I'll give you a minute to think about it. Okay, so what is the answer? That's right. It is the inorder traversal. Raise your hand if you don't see why this is the right answer. How many of you made a small tree and actually tried to construct traversals? Well, those of you who raise your hand probably know the answer. Make a small tree and construct the traversal. So I'm going to give you a tree here. I want you to write down all of these traversals. Okay? Okay, so here's a tree. I'm going to give you a minute. I want you to write out all the traversals, the inorder traversal, the postorder traversal, and the preorder traversal of this tree. Right? There aren't that many nodes there. Right? So it's 7 nodes. Go ahead and do it. I'll give you a minute. Because once you do it, all of the answers that all the questions I'm going to ask you should be pretty easy to answer. Question. What is the first key printed by the in-order traversal? Is it 7? Is it 42? Is it 60? Give you a minute to answer this question. What is the first key printed by an in-order traversal? What's the answer? What is the first key printed? It's 7 because it's printing in sorted order. So these two answers are consistent. So how does the in-order traversal work? Let's go back to what it's doing. It starts at the root. Then it does an in-order traversal starting from the left. So go to the left. In-order traversal starting from the left. Then it goes there. In-order traversal starting from 7. Again, it's going to make a call to the left, which is null, so that returns. Then it prints, so it's going to print 7. Then it's going to go to the right, which is null. Right? So that is basically printed 7. So as you do this in-order traversal, starting from the left, it's going to print 7. Okay, now, question. What is the first key printed by the postorder traversal? Same options. Right. So, I'll give you a minute. What is the first key printed of a post-order traversal of the above tree? It's not that complicated. All you have to do is run that snippet of code on this tree. Okay, so what is the answer? That's right, it's still 7. It's still 7. Because the logic that I gave for the in-order traversal still holds. What happens is, if you look at the post-order code, it makes a recursive call to the left. So starting from the root, it makes a recursive call to the left. Then it makes a recursive call to the left again. Now both the children are null. So both the child calls from here return null. So it prints nothing, and then it prints 7. Right? So both the in-order traversal and the post-order traversal both print 7 as the first key. So what's the difference between these then? What about the second? What's the second key printed So for this, it should be obvious what the second key is, because if you believe that it's in sorted order, the next key to be printed should be 10. But what about the first key printed by the post order, second key, sorry. Yeah? 15. Raise your hand if you see why the answer is 15. Okay, good. So most of you are following that. Second key printed is 15. The first key is 7, the second is 15. So it seems like a rather strange ordering. But the second key printed by this is 10. Why is that? Because if you look at the in-order traversal, starting from 10, it made a recursive call to 7, printed 7, then it's going to print 10, and then it makes a recursive call here, so on and so forth. Now you might say, so what's the point of the in-order, of the post-order traversal? I'm going to explain that to you shortly. But if you have any doubts after this lecture is done, because everything looks like it makes sense when I'm lecturing, and then you go back and it doesn't make sense, answer these questions. And the easiest thing is to take this tree, write out all 3 traversals, right? And you basically you'll see the pattern over here. So, okay, so here's my next question. Given the in-order traversal, meaning that suppose you just see the print statements. Just think of the prints, the output printed. Can you reconstruct the binary search tree? Okay? So, yes, no. Green is, which you can honestly use, is I don't understand. Meaning I don't understand the question. Okay, so I'm just saying, suppose I do an in-order traversal of a tree, I show you all the keys written down. Can you reconstruct what the binary search tree was? Does the question make sense? I want you to figure out the tree given the traversal. Can you do that if you're given an in-order traversal? I'll give you a few minutes to think about it. Okay, so what's the answer? Good, so most of you correctly said that the answer is no. And maybe the easiest way to see this answer is just to look at the first question. So if you truly believe that the in-order traversal prints it in sorted order, if I gave you 2 different trees on the same set of keys, 2 different BSTs on the same set of keys, you'll get the same order. Just to give you a simple example, let me give you 2 BSTs, 3, 2, 1. That's a BST. And 2, 1, and 3. In both of these trees, the in-order traversal is 1, 2, 3 because it prints in sorted order. But you cannot, looking at the order, determine which of these trees it was. Right? This is probably like the simplest example. I mean, you can even take an example with 2 nodes, which does this. But hopefully this gives you a sense of the structure of the tree cannot be determined by the in-order traversal. Yeah, does that make sense? But the in-order traversal is really useful because you can now sort the tree. So if I give you a binary search tree, again, common interview style question, given a binary search tree, print all the keys in sorted order. How do you do that? The answer is do an in-order traversal. What is an in-order traversal? It's these 4 steps. Okay? You need to remember this, right? In-order traversals, print in sorted order. Common question that is asked to check, like, do you understand BSTs? Yeah?
Can you explain the point of the preorder and postorder?
Sure. Yes, I'm coming to that. Question, given the post order traversal, can you reconstruct the BST? I should say post order traversal of a BST. Question makes sense? The same question I'm saying, suppose I gave you the post order traversal of a binary search tree. Can you reconstruct it? This requires a little bit of thought. Maybe a little more than a little bit of thought. So if I gave you the post-order traversal, while you're thinking, I'm just going to write down the post-order traversal of this tree here. Right, so it's a little tricky. Okay, so what do you think the answer is? So, okay, few of you, there's some yeses, some nos. Okay, so let me give you a hint. Let me first ask you this question, and you can use this example over here where I've given the post-order traversal of this tree. In a post-order traversal, what is the last node that gets printed? The very last node that gets printed. Yeah, in the back? The root node. The last node that gets printed in a post-order traversal is the root. So this is interesting because you can simply do a scan and you can figure out where the root is. Whereas if you look at an in-order traversal, you have no idea where the root is. Okay? Okay, so the answer is yes, but I want you to figure out why that is the case. I'll give you a few more minutes. So the hint is the last node is the root. That's hint number 1. And hint number 2 is use recursion. So you know where the root is. Once you know where the root is, can you figure out all the nodes of the left subtree and the right subtree? Okay, so I'll give you a few minutes to think about it. Don't think about like how to insert or something. Just figure out what the structure of the tree is. Okay, I'll give you a few minutes. Remember, well, 3 hints. Hint number 1, last node is the root. Hint number 2, what is the left subtree and right subtree? What are the nodes of the left and right subtree? And hint number 3 is recursion. All right, do you see the idea? Yes? Someone want to tell me what the basic algorithm is? Yeah, go ahead. Okay, you would swap them, but I want you to reconstruct the tree, even if you don't do it with code, even just how to do it on paper, right? Just on paper, yeah? Are you guaranteed to get the same tree? Can you prove it to me that you're going to get the same tree? Well, insert, who knows how this was created. There could have been multiple ways of creating this tree, but okay, I mean, yeah? Okay. In the back? You mean the root? Yes. More than 42, yeah. Yep. Okay. Okay. They also had their hand up. Yeah, go ahead.
I noticed that okay, it's kind of hard to explain. So 60 and 10 are the children of 42.
Okay, why?
Because I can't really say why, but I just noticed that it also follows that pattern for the other nodes. So 10, for example, the children are 11 and 7. So I think you could possibly manipulate the indices to, reconstruct
Okay.
the tree.
But 10 is the last node. Yeah. Yep. Recursion. How do you know which is the left half and the right half? Yeah, so how do you find that point? That's where the left tree ends. Yeah?
I have a base case, I think. That's all I got, though, is if the number is less than the root, then return, and then you reconstruct it to the right every time? Or come back to me.
So, the person in the back basically said, well, I guess said the answer, but maybe it's worth expanding on what was said. So in a postorder traversal, let's say that whatever was here was x, right? So you know that x is the root. And you know that the left subtree was printed before the right subtree. That's always the case in all of these, right? The left is always printed before the right. And all the keys to the left are smaller, and all the keys to the right are larger. So if you look at what this is going to look like, there are going to be a bunch of keys here that are less than x and a bunch of keys here that are larger than x. Right? And so all of this, so your tree is going to be x, and then something here that I call capital L, and something here that I call capital R. Capital L is the left subtree, capital R is the right subtree, and what you have here recursively is the postorder traversal of L, and here you have the postorder traversal of R. So if you just use recursion, so recursively, if you assume, I say inductively probably, it's like doing a proof by induction, right? You know that there is a procedure, like in induction, what do? You assume that you can solve problems for smaller settings, and you see how to construct the solution for the bigger setting. So over here, if you make x the root, then recursively apply your algorithm to get the tree L given the postorder traversal. Recursively apply the algorithm to get R from the postorder traversal, then you just join them together. What someone said about inserting in that order is also correct. But to me, that's a little less transparent than this. That's probably more efficient. But if you look at this procedure, you can kind of see how the structure can be read out from the tree itself. So what someone said about the children of x, that's right, the children of x are going to be the last node in each of these portions, right? Because this portion is the postorder traversal of L. So that child must be printed there. And similarly, this portion here has the postorder traversal of R, and so that must be over there. But instead of trying to have a piece of code that explicitly goes and figures all of those things out, you can just use recursion to automatically do it. Okay, it's like the magic of recursion, right? Because you know that you have recursive subproblems, so you can just call your procedure on those. Is this making sense here? Right? So at least hopefully you see the logic, right? And if you go and look at this example again, what we know is that this is the portion that's greater than 42, and this is the portion that's less than 42. So what we do here is you'd say, okay, 42 needs to be the root. Now you have to get L and R. So this is L and this is R. Let's now go and reconstruct L. So we know that the root of L is 10. Okay? And then you have the portion that is less than 10 and greater than 10. So 10 is going to be the root of that. And then the portion less than 10 is 7. That's just a single node. So that's just going to be 7. Then you have to construct, given 15 and 11, what that tree looks like. And again, the root of that tree is the last node, so that's 11. Does that make sense? And so then you would get 11, and you would get 15. The same logic is true for the preorder traversal as well. In the preorder traversal, the first node printed is the root. In the postorder, the last node is the root. But for someone who asked, what do you do with these traversals? This is what they're useful for. Given the traversal, you can reconstruct the tree. So in the binary search tree code that I've given, I think I may have given these traversals. The reason I give these traversals is if you write a piece of code, how do you know that what your tree is actually what it's supposed to be? So you print out the preorder traversal, and then you can draw the tree. Does that make sense? If you print the inorder traversal, you will not be able to see what the tree looks like. But if you're given the preorder or postorder, either of these, you can reconstruct the tree from them. Yes? In which part? Here?
Yeah, so how do you know 11 is going to be?
The root of this portion. So, okay, so this portion here is the post-order traversal of some tree. And in any post-order traversal, the last node is the root. And because there are only two things printed there, the last one is the second one. It's not the second one, but it's the last. It so happens that there are just two nodes there. Right? So if you, for example, in this portion here, the 7, 5, 11, and 10, that's this subtree here, the last node is the root. And the overall, the last node is the root. So as long as you identify portions that are subtrees, note that 15, 11, 10, and 50, this portion is not a subtree. Right? This part over here, from 15 to 50, is not a subtree. That's just like different portions. The way that you get to a portion is you figure out what a root is, and then you say, okay, everything less than it is one portion, everything greater is another portion. Those are the subtrees. Does this make sense? Question?
How would you actually be linking the subtrees back to its root? Is it in the base case of some sort?
So if you were to write, okay, so let me sketch something out here, and then we'll see if, so suppose you want to you want to reconstruct. You want some procedure that reconstructs. And let's just say that what it returns, it's going to return some node, which would be the pointer to the root of the reconstructed portion. And over here, what you get is, think of it as what you're getting, in this setting, you're getting like an integer array, right? Because you're getting a traversal. And so let's just say that in array is, I'll call the post order. Right? So you're getting the post order traversal. So you'll say that if the length of the post order is 0, then you just return null. Right? Otherwise, you'll say so I'll say the int, the root key is going to be post order of the length minus 1, right? It's the last element. That's the key that's in the root. So then what you would do is you would create a node. So then I'm just going to write this as comments, like create a node with root key called root. So I'm just going to call this, okay, so maybe root is a bit confusing. So I'll call this okay, so I'll call it the intermediate root, because I don't want to confuse it with the root of the whole tree. So I create some node that's the intermediate root that would have whatever key I've discovered at the end. Right, then I would say that node star left child is equal to the post order of the left post order, and then node star right child is equal to the post order of the right post order. And to figure these things out, you're basically going to find everything that is greater than the root key and less than the root key. Right? That gives you the left and right post order. And then you would do, sorry, I'm going to write over here. I'll just say that inter root arrow left is equal to the left child, and inter root arrow right is equal to the right child. right? So then that does the linking. Does that make sense? So this, I guess this would probably just do it. The only thing that I've not written here is that you need some kind of for loop to find out where this is. Yes? I'm sorry, say it again. Sorry. Yes. I'm sorry, reconstruct. Yes. So let me see if the problem with this is that you actually have to traverse this array to find out where the split is, and so that is an extra like linear time overhead. I believe this can be done, and I think that if you instead sort of it turns out that if you were to insert the keys in that reverse order, you would reconstruct the tree. And I think maintaining pointers, you can just build the tree in linear time then. This procedure here would not be linear time. But I think that conceptually this is a much more clearer picture than the process of inserting in reverse order. Yes?
Your if statement says if length of postorder is, what is the last order?
0. Right? If the length of the post order, that's just the base case, right? That's just saying it's null. So this is the logic. So I would recommend, I'll write this over here because if you take notes, code it up, and then you'll really understand it. Like, I have not written the code for this, nor is it part of a test, but it's sort of a classic procedure on reconstructing a tree given the post-order traversal. And the same works for the preorder. Actually, it's probably even more transparent. Instead of the root key being the last element, it's the 0th element, like the first element, or whatever, 0th, the beginning of the array. Right? It's the opposite picture, right? So this node, so in the case of the preorder, you would kind of split it that way. This would be the root key. Okay? Does that make sense? The best way to understand the more complex data structure like a binary search tree is to draw lots of pictures and like run these algorithms sort of on paper for a small tree. So you could use a tree with like 6 or 7 nodes. Okay, it's very hard to understand this abstractly, right? Even though I sort of teach it abstractly, because I want to teach you how to like code it and do things, to understand it, you need to draw these small examples, run them on paper, and then they'll start becoming clear. Okay? And once you get it, there's really nothing more to know about traversals, frankly. The in-order traversal gives you the sorted order, and given the pre- and post-order traversals, either of them, you can reconstruct the tree. So it's like the basic thing. Maybe one thing that I should have said, which I did not, is that the running times of all of these traversals is just theta of n, where there are n nodes in the tree. Because what these procedures do is that they visit every node essentially exactly once. Right? They go to each node, and if there are n nodes, it runs an O of n. All right? Yes?
So like, I don't know if this analogy is correct, but like for like post-order traversal, like could you imagine as like taking a strip of paper, cutting it in half, and then like for that one split, you take the right one, and you continue to do that?
Yeah, no, that's exactly what's happening here. That is the correct analogy. Like this way in which I've cut it up is what you could do it. You could do it on paper, and then you would essentially build the tree that way.
And then the pre-order would be like with the left.
With the first node, right? The first node is the root, and then you break it up into 2 parts, so on and so forth. Yeah, no, that analogy is accurate. It's accurate. Okay, so let's take a break for a few minutes, and then when we come back, we'll do self-balancing trees then.